Yes.
This exercise is related to nuclear decay and the binding energy. We'll start with question 25. Question 26 we'll start with. In this question, one method for sterilizing a metallic surgical instrument is irradiating them. The instruments are sealed in a plastic packages and then passed in front of the radioactive isotope. By considering the relevant properties of each type of radiation, determine whether alpha, beta, or gamma radiation would be the most appropriate for this method. So if you want to compare which one is suitable, like let's talk about alpha. Alpha is highly ionizing radiation, but it cannot penetrate more than few centimeter of air. So that's why alpha will not be suitable. What about beta? Beta is having a moderate ionization, therefore cannot penetrate the metal instrument because it can be stopped by few millimeter of aluminium. So it's unsuitable. Where gamma is it has a least ionizing ability, but it has a greater penetration. Even it can pass through thick lead. So it's a most suitable because it will penetrate through the packaging and the metallic instrument. So for the sterilizing the equipment, gamma, the metallic equipment, gamma is more suitable as compared to beta or alpha. So the points which you have to relate the ionizing ability and the penetration. Alpha, the highest ionizing, but the least penetration cannot pass through. Beta, moderate ionization and penetration, but it can pass through thin aluminium, cannot pass through aluminium. So it's not suitable. Gamma is the least ionizing but greatest penetration. So a long-term exposure can sterilize the instrument, metallic instrument. Next, we have in a part B, a radioactive isotope commonly used as a source of radiation has a half-life of 5.27 years. After every 5.27 years, the radiation will change into half of its original value. A sample of this isotope contained 5.02 exponent 23 unstable nuclei when it is new. Show that the activity of the sample when it is new is about 2 into 10 to the power 5 becquerel and 1 year is equivalent to 3.15 exponent 7 second. So we have the formula because if we need an activity, the activity, there are two formulas for activity we can use, like A is equals to lambda n, that is one of the formula. Another formula for activity, it's a change in number of a nuclei in a unit time. We have the half-life, as I already mentioned, the half-life. So using the half-life, we can work out the decay constant because lambda is equals to 0.69 ln2, or you can also write 0.693 divided by t half. Or half-life is 0.693 over lambda. So we'll have 0.693. The time, the half-life, they mention it is 5.27 years, but we have to convert into seconds because the unit of activity is like rate of change of a nuclei every second. So the becquerel, the unit becquerel, the time should always be in seconds. Then we multiply by 3 point, because 1 year is equivalent to 3.15 exponent negative 7. So we multiply, this will give us the value for decay constant, 4.18 exponent negative 9. Then after working out the value of a decay constant, we are finding the activity. As we know, activity is what? Activity is, it is delta n by delta t or lambda n, where lambda is the decay constant, which is 4.18. But we put a negative sign here just to show that the activity always decrease. It's optional because the calculation, what is important? 4.18 exponent negative 9 multiplied by 5.02 into 10 to the power 13. So when we simplify, we got 2.09 into 10 to the power 5 and second inverse. So that is because the becquerel or second inverse, how many radioactive nuclei decay? The activity of a sample decreases over a time. Like in the beginning, it is having a high activity, but it decreases. Calculate the time in year until the activity become 8 kilobecquerel. Here, we were having original activity as 2 exponent 5 becquerel. Because they mentioned that calculate the time in years, so when we substitute the half-life should be in years. So original activity, like the new activities, original activity, e raised to the power minus lambda t. That's a formula. So we need this time. So A is equals to A naught e raised to the power. So when we substitute like the new activity is 8 kilobecquerel, so it will be 8 into 10 to the power 3. Original activity was given in the question 2.1 into 10 to the power 5 minus lambda. What is the value of a lambda? We calculated a value of a lambda in second. So we can substitute right now in seconds. So we'll get time in seconds. And then once we get the time in seconds, we'll convert into years. So if we substitute, because it was 4.18 into 10 to the power minus 9 multiplied by t. This will go there in division. So this will be 8 into 10 to the power 3 divided by 2.1 exponent 5 e raised to minus 4.18 into 10 to the power minus 9 t. We'll take ln both sides because when we take ln, e will cancel out. So ln of this value, and so we'll have ln 8 into 10 to the power 3 divided by 2.1 into 10 to the power 5, and this will be minus 4.18 into 10 to the power minus 9 t. So if we need t, this whole will go there in division, we'll get the value for t. So t is about 7.84 into 10 to the power 8 second. The second will convert into years, because you mentioned 1 year in the beginning of question. They mentioned 1 year is equivalent to 3.15 exponent 7 seconds. So we'll just simply divide, as a 1 year is equivalent to 3.15 exponent 7 years. So we just divide that. So it will be 3.15 exponent 7. So it will be about 24.9 years. So it will take 24.9 years to change the activity from 2.1 exponent 5 to 8 exponent 3. Is it clear, this one?
Yes, sir.
Any doubt in this?
No.
Next is a technician is checking the activity of a radioactive source. Describe how a technician should safely handle the source. If you are handling a radioactive source, what we should do? we should always use tong or forceps or tweezer should be used. And the exposure time should be minimum as possible. And the source should be stored when it is not in the use, it should be stored in a lead line box. And it should not point um, up towards the people, like the living tissues, living. So a technician should use the long forceps, should not point towards the tissues, soft tissues, as well as keep in a lead line box when noticed, not in use. Question 27. Americium 241 is an artificially produced radioactive isotope which was commonly used in smoke detectors. In decays through emission of alpha particle to neptunium. Complete the nuclear equation for which represent this americium decay. Whenever there's an alpha decay, the nucleon number decreases by 4. So this will be 237. And the proton number decreases by 2. So this will be 93. And we'll have, this is a symbol for alpha with the representation 4 and 2. Why is most of energy released in a decay become kinetic energy of alpha particle? Like when this decay releases, because both like it's releasing energy, but why the energy releases or kinetic energy of alpha particle? So the main reason, like most of the energy gained by the alpha particle in the form of kinetic. So first, what will happen? Because in this decay, because whenever a decay happen or occur, the momentum should be conserved. So what is the starting momentum, initial momentum of the nuclei, americium nuclei? That is 0. So what should be the final momentum? The final momentum should also be 0. So how the final momentum is 0? If the neptunium is moving towards the right-hand side, the alpha particle will move towards the left-hand side to conserve the momentum, because if one particle move towards right, another should move towards left-hand side. So because of conservation of the momentum, the alpha particle and the neptunium will move in opposite direction. Then because the mass of neptunium is high, so its speed will be less because the product should be same. Where mass of alpha particle is low, so it will move at a high speed. And the kinetic energy is half mv square. Like kinetic energy increases with a proportional square with the velocity. So if the velocity is double, the kinetic energy will be 4 times. So how we relate here, we'll mention, or you can also compare Ek is equals to P square over 2m. You can also use this equation. If they have the same momentums, the relation between mass and kinetic energy is inverse. The one which is having a smaller mass will have a greater proportion of kinetic energy. So how to relate this? You will mention that the momentum will be conserved in this decay. So if alpha particle and neptunium will move in opposite direction with the same momentum, and the momentum is inversely proportional to mass, the kinetic energy is inversely proportional to mass if the momentum is constant. So the alpha particle is having a lower mass, so it will have a greater kinetic energy. Is it clear, this question?
Yes, sir.
The next we have the table gives the masses of americium nucleus and its constituent particles. It's given in U, atomic mass unit. Calculate the binding energy of americium, which is, so if we need the binding energy, first we'll find the mass of the nucleus, and then we'll find the mass of particles independently. And we take a difference of the mass because mass in the nucleus will be less, but independent it will be more. So when we take a difference of these two masses, what we call the mass defect. And after getting a mass defect, to get the binding energy, we use the formula E is equals to mc square. So mass defect into speed of light square will get the binding energy. And to get the binding energy per nucleon, binding energy divided by number of nucleon will get the binding energy per nucleon. But this is, the mass is in U. When you're substituting in the formula, it should be in kg. So you have to, a unit conversion is also important. Or you can also use the idea, first find the mass defect in U, and then convert, because 1U is 1.66 exponent minus 27 kg, which is the mass of proton, or in kg, or a neutron, you can also say. So first we'll find the mass defect. How we can find the mass defect? The mass of the nucleus. So, because we need a binding energy per nucleon. Americium, this is the mass of a nucleus of americium. And these are individual particles mass given. So mass of a nucleus of americium 241.00471. You have to use all these numbers. Don't round off, especially in mass defect question. Minus the mass of the nucleon. How many, like example, 95 was written for americium. The proton number was 95 and 241. So 241 minus 95 will give us 146. So this will be 95 times the mass of a proton, because 95 protons are there, and 146. 146 neutron will be there. So 95 times 1.0072628 minus 146 times 1.00866. When we simplify, we will get the mass defect. But that mass defect will be in U. So the mass defect is minus 1.95125 U. Then we convert 1 U is equals to 1.66 into 10 to the power minus 27 kg. So if we want to convert this, so we just multiply. So minus 1.95. Negative sign shows here that the mass has decreased. Like the O, when, because, or you can write the mass of a neutron and proton first. I wrote nucleus first, but you can also write like the total mass of a proton, Z times the mass of a proton, plus A minus Z times the mass of a neutron, minus the mass of a nucleus. That will give us the mass defect, this equation. So negative sign because I put the individual particle are at the last. So 1.95125 multiplied by 1.66 exponent minus 27 kg. When you simplify this, you will get the mass defect in kg, which is 3.24 exponent minus 27 kg. Now, after working out the mass defect, we'll find energy in joules. How much binding energy is there? E is equals to mc square. So this is 3.24 exponent minus 27 times the speed of a light, which is 3 exponent 8 square. So when you multiply, you will get answer in joules, which is 2.92 exponent negative 10 joules. Then binding energy per nucleon. The binding energy is 2.92 exponent minus 10 joules divided by 241 nucleons are there, the sum of neutron and proton. So when we divide, we got 1.21 into 10 to the power minus 12 joules. That's how much binding energy is used for one nucleon. Is it clear discussion?
Yes.
Next is this repeated question related to the graph for binding energy per nucleon in mega. The graph shows the binding energy per nucleon with nucleon number for a range of a nuclei. Use the graph, explain why the fission for nuclei with a large nucleon release large amount of energy. So, why the fission of a nuclei with a large nucleon number releases a greater or large amount of energy that we have to state. So, it's always a structure answer. First thing, we explain the fission, okay? So, what is a fission? The fission is actually a breakdown or a splitting of a heavy nuclei to form lighter, smaller nuclei or lighter fragments, we can say. So, as a result, the binding energy will increase. Like the fission fragments are higher up in the binding energy because in a fission, when a fission happen or occur, the nucleon number decreases like for in fragments. So, and they try to reach iron. So when the nucleon number is decreasing, the binding energy per nucleon increases. And whenever binding energy per nucleon increases, it means the reaction is exothermic, like it will release energy. But why heavy is releasing more energy and lighter less? As you compare, like if I compare this one with this one, so this is the energy difference. But when I compare these two, this is the energy difference only. So it means, or the graph shows that for increase in binding energy per nucleon is very small for the heavy nuclei but for a large number of nucleon which undergo a fission means overall energy release will be large. Because for usually why fission releases less energy and fusion releases more energy? Because when the fusion happen, see, when one fusion happen, this is a difference. But when one fission happen, this will be because this convert into this, and this example convert not zero, I mean one here. Let's say this converted into this. So this is a difference. So increase in binding energy is more, so the energy release will be higher. Here, what will happen? Increase in binding energy will be less. Even the heaviest nuclei will undergo a fission, break down, but this is an increase in the binding energy. So increase in binding energy is low. So as a result, less amount of energy is released. But usually what happens, because we have a large number of a nucleon, so fission reaction, why the graph is, even this part is, even you don't include, that's fine. It just give an idea that if we have no nucleon, they don't have any binding energy in the nucleus. So nucleus with zero nucleon will have zero binding energy. That's just the significance. But we have a large number of a nuclei, so as a result, even though one nuclei releases less energy when it undergo a fission, but a fission is a chain reaction, so multiple nuclei break down. So as a result, the overall energy release will be higher. So how you summarize this? First thing, you will explain the definition of a fission. Then you will mention that when a heavy atoms undergo a nuclear fission, the binding energy per nucleon increases. As the binding energy per nucleon increase, what will happen? But in a fission, when a heavy breakdown into lighter, a small increase in a binding energy, so it releases energy. But fission is there are a large number of the nuclei. So fission is actually a chain reaction. So overall, greater amount of energy will be released. Like one will release less, but there are many. So that's why overall it will be large. Is it clear? Because if you compare one here, one undergo a fission. Let's say this is 7.8 and this is about 8.8. So this is 8.8, this is 7.8. So it's only 1 mega electron volt. But if you have this is for one, but in a fission, we have many. So it's like maybe if 2000 are there, So it will be 2000, overall 2000 mega electron volt will be released because one is releasing 1 mega, but a fission is a chain reaction. So overall energy release will be higher. Question 28, carbon 12 is the stable isotope of a carbon. Most common exists in this form. Carbon 14 is formed in the upper atmosphere. Carbon 14 is radioactive and decay randomly by emitting a beta. Carbon 14 is formed when nitrogen nuclei absorb a neutron. A nuclear equation is shown. So what is X? So neutron does not have any charge, so 1 and 0. Total, this is represent because no proton is there, 7 plus, like total should be same on both sides. So this is 6, so 7 now, and 15. So if we put 1 and 1, so which atom is having 1 and 1? So that is hydrogen. Because the total nucleon number and the proton number on the left hand side of equation matches with the right hand side. What is meant by random decay? So random means like there is no order. About X, you can write about this can be hydrogen or you because hydrogen is having one proton and no neutron, or you can also say it's a proton as well. A nucleus, a proton could it's also acceptable. We cannot know like which will be the next atom decay. Cannot know which nucleus will decay next. That's meaning of random. The carbon 14 is taken by a living organism through their lives, and organisms is alive. The ratio of a carbon 14 to carbon 12 stays the same. From the time the organism die, the ratio of a carbon 14 to 12 decreases. Hence, certain ancient objects can be dated using this carbon. That's also called carbon dating, like using the percentage. Because when organism is living, its intake and giving out this carbon 12 and 14 ratio, like in the body, remains the same. But once it died, there's no intake for the carbon 14, so the carbon 14 to 12 ratio start to change. The activity time for a graph for carbon 14 is shown. Use a graph to show that the half-life is about 6,000 years. So half-life is actually a time taken by half of the radioactive nuclei to decay. So if you're taking as 150, this is 4,000. 10 boxes equals to, so this is 4,000. Because you can take any value, it's not, you can start with 200 as well. 10 boxes equals to 5,000, each is 500. So this is 1,500. And this is 6,000, 7,000, 7,500. So it's 7,500 minus 1,500. So what you will get 6,000 years. That is the half-life. Any value you can take 150, 75. It will give the same result. A scientist is trying to determine the age of ancient wooden object. A sample is prepared from this object is corrected. Count rate to 10.9 becquerel. The count rate of a sample obtained from a living is 29. Two samples have the same mass. Why the count rates have to be corrected? Like why we should always use a corrected count rate? Because Um, the idea is that because there will be background radiation will change will increase the recorded count rate, and background rate has to be subtracted from the rate, like because we want to find from the sample. So that's why the background radiation will increase the recorded count rate. So it will affect the results. State one procedure that would increase the accuracy. So for these experiments related to radioactivity, if we want to improve the accuracy, we should record for a longer duration of a time. That is one thing, and repeat the counts and find an average. Calculate the age of this ancient object, how we can work out the age. How we can work out the age of this ancient. So activity is given. Originally it was this. Now it is 10.9. So A is equals to A naught e raised to power minus lambda t. The current activity is 10.9 becquerel, corrected one, and the original activity was 29.6. E raised to power minus lambda, what is a lambda? The decay constant. How we can work out because lambda is not known, so we can work out lambda. Lambda is 0.693, like ln2 divided by t half. So it will be 0.693 divided by the half-life, which was 6,000 years. So that will give us the value so we can just substitute here 0.693 divided by 6,000 into t. Then this will go there in division. I'm solving it here. So it will be 10.9 divided by 29.6 is equals to e raised to power minus 0.693 over 6,000 into t. Then we take ln both sides. So this will be ln 10.9 divided by 29.6. This ln and e will cancel. It will be minus 0.693 over 6,000 into t. Now this value will be negative, so negative cancel with negative, and just the final answer, like after working out ln 10.9 divided by 6,000, this will be separate, multiply by divided by 2.9, 29.6, I mean, into 6,000 divided by 0.693. That will give us the value for t. The time for this sample, like how much time it will take to change from activity 29.6 becquerel to 10.9. So this time will come out as 8649 years. This is the time it takes to change this activity. And it will be years because we took the first value, like the half-life was in year. That's why this is also in years. If the half-life was in seconds, this will be in seconds as well. New reports claim that the dinosaur skull has been found and suggest that the skull is 68 millions years old. Like this is 68 into 10 to the power 8, 10 to the power 6, I mean, million years. Explain why carbon dating could not have been used to determine the age of this skull. So why we cannot use a carbon dating? First thing, if you compare, like the half-life of carbon is 6,000 years. After every 6,000 years, the carbon will break down, like changes to half of its original value. So this duration, like the age of the skull is very long as compared to the carbon half-life. So as a result, what will happen? Because after every 6,000 years, the amount of a carbon-14 will become half of its original value. So as a result, the activity will fall to a very low value. So like the activity will be too small to measure in this total interval. That's why we cannot use this carbon 14 for determining or confirming that the age is about 68 exponent 6 years. So we use always a sample which is comparable. It's with a comparable half-life, not very short half-life, and the duration is long. In that case, it is not suitable. In part E, the website includes the following statement about a heavy nuclei. Particles in the nucleus are held together by a strong scientist called a nuclear binding energy. It is possible to overcome this binding energy in some large atoms such as uranium using the using the atoms to undergo fission. Comment on this statement. So first thing, when you compare, you have to relate the sentence here. So binding energy, what is the concept of a binding energy? The binding energy released when the nucleus is formed or the nucleus split into like when a fission happen or a fusion happen, the binding energy is released. Binding energy is not the force. Binding energy, like what is a mistake in the statement here, that the particles in a nucleus are held together by a force scientists called nuclear binding energy. That's wrong. That is not that statement is wrong because it's not, it's actually strong nuclear force which is binding the nucleus, but binding energy is the energy released when the lighter nuclei join to form heavy or a heavy nucleus split. So when a fusion or a fusion happen. And binding energy is not the force. And basically we don't overcome the binding energy. And atom do not undergo fission, but the nuclei does. Like it's written here that causes atoms to undergo fission. That is why, what is the mistake here? Atoms does not break down. The nucleus inside the atom will break down. So the nucleus undergo a fission reaction. And fission is when a massive nuclei split into a lighter nuclei. So how you score the marks here? First thing you will mention a binding energy is energy released when a heavy nucleus break down into a lighter or a lighter join to form heavy. So first thing, the particle in a nuclear held together by a force called nuclear binding energy. No, that is not nuclear binding energy. Binding energy is energy released when a heavy nucleus undergo a fission or a lighter nuclei undergo fusion. And it is possible to overcome binding energy in some large atom. No, it's not possible. Like we don't overcome the binding energy. It's just the binding energy of a nucleus changes. When the binding energy of a nucleus changes, it releases energy. And when the binding energy increase for a nucleus, it just release energy. We don't overcome the binding energy. Like if we say we overcome the binding energy, means we destroy the atom. Like if I say I overcome the binding energy of an atom, it means I have destroyed the atom. But we don't overcome the binding energy. It's just a binding energy is changed when a fission or a fusion happen and it release. And that cause atoms to undergo a fission. Atoms does not undergo fission. A nuclei of an atom undergo fission. So this is wrong. This statement is we have to go, and this we cannot overcome. This is wrong, and the atoms does not undergo fission. It's the nuclei which undergo a fission reaction. Is it clear, this one?